we're now going to look at some worked example problems. So these are basically hand-worked. That is, I'm kind of doing it step by step. I'm also going to have a separate video that goes through and does some MATLAB examples, where we're looking primarily at how to use MATLAB to do these things. All right, so example problems. Here we go. So we start off with this system. Notice it's an unforced system. There's no input. We start with this matrix, and we start with this initial condition. So here is a matrix. So x of t plus 1 is equal to a times x of t. We start at this initial value, and so basically x at time 1, if we plug t is equal to 1 here, is equal to this times this, and so you can see we're probably going to get something different than this, and so forth. We just keep going, and each time we're going to multiply by this to get the next solution, and so we can go through and iterate this. And so here I have 3 values, and so as I iterate this, I'm going to see those values. So here they are. So let's see, blue is the first state, green is the second state, and red is the third state. So initially they all started at 1, 1, 1, 1. So they all started here, and then as time goes on, they bounce around and do other things. So it looks just like a jumbled mass here going on. So I can go ahead and connect the dots just to kind of help me see what's going on. And it looks kind of, the response looks kind of sinusoidal, somewhat sinusoidal in it. So each one is like a sampled sinusoid, and actually it is actually a sampled sinusoid. It's actually a decaying sinusoid. It's being sampled. Okay, so that's actually what the response is, and so seeing it with the dots connected kind of helps that way. Now, because there are actually 3 variables all going at the same time, I can actually get a response plot of the system in 3D. That is, each dimension corresponds to a separate state. So here's the response, what it looks like in 3D. So here's state 1, x1, x2, and x3. And so this is actually where we start, 1, 1, 1. And you can see how it goes. And it's basically going, remember we said it was a sinusoid, it looks sinusoidal somewhat. It is kind of sinusoidal. It's kind of doing a spiral. Okay, it's kind of doing a spiral here, and so so that's actually what's going on in this thing. So it's kind of a pretty little pattern there, and so this is actually generated in MATLAB. In MATLAB, you can actually pan and tilt and zoom and so forth, so you can actually see what it looks like. This action, it turns out, actually happens in a plane. This thing is actually happening in a plane in the entire space. It's not just bouncing around randomly. It's actually doing so in a plane, which is kind of interesting. Okay, the next example, we have this matrix, and we can go through and calculate and show that this is the state transition matrix. Okay, so I'm not gonna do that right now, but this is the state transition matrix. So a to the power k. If we actually look at it in this form, a to the power k minus l, wherever we see k, we basically substitute k minus l. So you can see that we actually, for some matrices, we can actually get sines and cosines of our time variable k. In this case, we can actually get. Sometimes I'll use t for the time variable. Sometimes in discrete time I'll use k for the time variable. So the reason for using k is because it goes way back to the days of Fortran programming, when the variables I, j, k, l, m, and n were all declared to be integers. Okay, they were all declared to be integers, and so you'll often see I, j, k, l, m, and n being used to represent integers. Okay, and it goes way back to Fortran programming. But anyway, here we have this expression, and if we look at the properties of the state transition matrix, so a to the power k minus l, notice that the state transition matrix, if we evaluate it when these two are equal, When those two are equal, corresponds to when we have a to the power 0. So if you plug in 0 here, notice that cosine to the power, cosine of 0 is 1. 2 to the power 0 is 1. So this quantity is 1. Sine to the power, sine of 0 is 0. Divided by 1 is 0. Here I have 0 divided by 1 is 0. And 1 divided by 1 is 1. And so we get, in fact, the identity matrix. So again, we can evaluate things this way. I have, in the note, in the lecture, shown an example of using the transform method for solving this. All right, forced solutions. So here I have a state model, discrete time. I can go ahead and plug this into MATLAB, and I'll show more of this later, but I can define A, B, C, D matrices, and I can use the step command. The step command basically applies a step input to each of the inputs. This is the multi-input system. So it applies a step input to each of the inputs, and it looks at the response of that step input at each output. So here we have 2 inputs, and here we have, because we have 2 columns. Here we have 2 outputs because we have 2 rows. And so we have 2 inputs, 2 outputs, and so we would actually get 4 plots altogether. One for each input associated with each output. And so the result looks like this. This is what the result looks like. So notice that this value just remains 0. That is, from input 2 to output 2, we get 0. So input 2 does not affect output 2 at all. So, which just means it's not connected. Even though it wasn't obvious that that was the case by looking at the matrices, it actually ends up being the case. So that is the time response. Now what about computing the state transition matrix? Well, as I mentioned, we can use transforms to do this. So if I take this matrix and I form this quantity I minus QA quantity inverse, so here's I minus QA, taking the inverse, we get this expression. There should be an inverse here. We get this expression. And so performing partial fraction on this, if we use this transform pair, A alpha to the power k is equal to 1 over 1 minus q alpha. If I multiply this by, let's say, 2, I'm going to get a 2 out front here. And so each of these terms is of that form. Notice that this term, my alpha is 1, so 1 to the power alpha, 1 to the power k is just 1. So we'll get constant terms appearing here, 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 and so forth, all the way throughout this matrix. So when we take the inverse Q transform, we see these constant terms appearing throughout here. Otherwise, we get powers of some number raised to the power k. And these powers, you can go through and show, are actually the poles. So the powers are associated, these things that are raised to the power k are actually the pole values of our system, related to the poles of our system. And so the poles, again, are when associated with when q, the value of q or the value of z in the z domain, where the denominator is 0. And so the poles, or the eigenvalues, the poles of the system are related to the eigenvalues of the matrix A. Okay, so what we have here raised to the power k are the eigenvalues raised to the power k. And so we basically have a linear combination of the eigenvalues raised to the power k. And each of the terms has a linear combination of the eigenvalues raised to the power k. And that's what we're getting here. Spectral mapping theorem, we saw that if we take A and compute the diagonal form of it, we can compute the function of the diagonal matrix in this process. So here we have a diagonal matrix, and the function of that will be expressed this way. It's a diagonal matrix that is formed this way. So we have this matrix, we take the diagonal form, we get the diagonal form of it. Now this is kind of a contrived example, I made it up, that's why everything's integers. In general, you won't get integers, okay? In general, you won't get integers. So this matrix, lambda to the power k, is this, and again, you can form this by taking this matrix, multiplying it by itself, the original A matrix, multiplying by itself, and you'll see that each of these elements only multiplies by themselves. And so if you do this k times, we will get this thing with these elements raised to the power k. And so a to the power k then is, notice the diagonal elements, which are the eigenvalues raised to the power k. And when I multiply on the left and the right by these matrices, I just get linear combinations of all those guys. Okay, and so you can see there's a bit of work here. If we do this in Symbolic Math Toolbox, it's not that bad, but you can still get some pretty nasty looking expressions coming out of all this. So here's our expression. Again, we can check if we let k be 0, wherever we have something to the power k, that will become 1. Okay, so 1 minus 2 is 1. 1 minus 1 is 0, and so forth. And you can go through and show all the way through that we end up with the identity matrix. Boom. So this again is a way of checking to see if in fact you have done it correctly. Again, using the Cayley-Hamilton theorem, we are looking for the functions g, and if we have non-repeated poles, non-repeated eigenvalues, I sometimes use them interchangeably, poles and eigenvalues, then this Vandermonde matrix is invertible, and we can get the g's from this expression. And notice that these g's are going to be a linear combination of the eigenvalues raised to the power k. That's what this is going to give me. It's a linear combination of the eigenvalues raised to the power k. And so that's what we get. So starting again with this matrix, we get the eigenvalue matrix. And so here I just get the eigenvalues for the sake of computing the eigenvalues. I don't use the eigenvectors like I did with the spectral mapping theorem. So at x is equal to 1, we have this relationship, 1 to the power k. Here's my functions. At lambda is equal to 1/2, I plug in this for lambda. Lambda is equal to 2, I plug in this for lambda. So these are my 3 equations. And g2, g1, and g0 are my 3 unknowns. And so I get this expression. Here's my Vandermonde matrix. So I solve for these functions as the inverse of the Vandermonde matrix times this vector. So again, this vector is the eigenvalues raised to the power k. And when I multiply this Vandermonde matrix inverse times this is the expression I get. So these are the functions of g that I get. g2, g1, and g0. And so the function a to the power k now is this matrix times a squared, this function times a squared, plus this function times a, plus this function times the identity matrix. And when you combine it all, you get the exact same function that we got before. So this is just an alternate way of doing that. So some methods, sometimes one method is more efficient, sometimes another method is more efficient. So again, for repeated roots, we need the derivatives to match. All right, so here we have an example of a matrix that has repeated eigenvalues. So notice the value 2 is repeated for this matrix. So this matrix is almost a Jordan matrix. No, it's a upper triangular matrix, but we don't have ones just above the diagonal. So it's almost a Jordan matrix, but not quite. But anyway, clearly it has repeated eigenvalues. Anytime you have a diagonal matrix, you have the eigenvalues along the diagonal. Anytime you have a triangular matrix, either upper triangular or lower triangular, the diagonal elements are the eigenvalues of that matrix. So here we have repeated eigenvalues. It's repeated 3 times. So if we have a function that we're going to be trying to take this function of this matrix, then we not only need the function, but we also need the derivatives. So in this case, we're going to look at this example function. F of x and t is e to the xt. Okay, so this is like what we would use in continuous time, but it's just a function of time. I could use cosine of xt or some other function of x and t. So e to the at is what we're going to be looking for eventually, but for now, e to the x. So this is a function of x. and x is eventually going to become a, and then we have another variable t here. Okay, so when we use this function now, when we evaluate the interpolation conditions, we're going to evaluate at f and also the derivatives. The derivatives, f prime and f double prime, are with respect to x, not with respect to t. Okay, so when we take this function, derivative of that with respect to x, we get t times this. When we differentiate this with respect to x, we just get another t. Notice that the t is just a constant as far as the x is concerned. And so we get these expressions for f and its derivatives, okay, that we need interpolating. So our interpolation conditions, we have g of x and t. So this is the form that's going to take. The coefficients are functions of t, and then we have a polynomial in x. Okay, this is just a polynomial in x. And so g prime, the derivative of this, is now again with respect to derivative with respect to x. And so x squared becomes 2x. Then this x just becomes 1. This term goes away. Differentiating this with respect to x, x appears only here, and so we get this quantity. So we have g and its first two derivatives, and then the interpolation conditions basically say these two need to be equal to each other at the eigenvalues. In this case, for these functions, we only have one eigenvalue, that is x is equal to 2, and so if we evaluate the function at x and t, in this case x being minus 2, we get this. Evaluating g at minus 2, we get this expression. So this gives us one equation. I have three unknowns, g2, g1, and g0. I evaluate the first derivative at 2 and t, and I get this being equal to this. And finally, I get the third interpolation condition. I get this quantity must be equal to this. And so I can stack these three equations into a vector equation. I can factor out the unknowns. Okay, so these are the quantities I have, and I get this matrix in between. This is my generalized Vandermonde matrix, and I take the inverse of this generalized Vandermonde matrix, and I get now the functions g. And so now that I have the functions g, my function, which is e to the at, so remember now f of xt is what we had before. I'm substituting x with a. So the exponential, the matrix exponential, is going to be given by this expression. So a is this, a squared is this matrix. Here's a to the power 0, which is the identity matrix. And so I add these three things together, and when I do that, I get this expression. So my matrix exponential for this matrix is this function here. So notice we're getting e to the power 2t, which are the eigenvalues. And again, we can check that the state transition matrix still holds for this. That is e, so when t is equal to 0, I get the identity matrix. So these are functions then of a square matrix, and we have now worked some examples. So have fun. Stay tuned to watch the video that shows how to use MATLAB to do a bunch of these kinds of things that we're going to be working with.